Hi, today we're going to talk about throttling Tor bandwidth parasites. We're going to look at a problem in the Tor network, which is a small fraction of users using a large majority of the bandwidth, and how to deal with those users by throttling them. I'm Rob Jansen from the U.S. Naval Research Lab, and I'm also a PhD candidate at the University of Minnesota. This is joint work with Paul Syverson from the U.S. Naval Research Lab and Nick Hopper, my advisor at the University of Minnesota. So the big problem in Tor is currently that there are a small fraction of users, shown on the left pie chart, the BitTorrent users, who are using a large fraction of the bytes available in the Tor network. Shown on the right graph, you can see that BitTorrent users are indeed consuming a large fraction of the available bandwidth. So these bandwidth parasites, the small set of users, is making the network congested for normal HTTP or web users, for a large majority of the users of the network. Okay, so this work is going to explore how can we throttle these BitTorrent users so that we can make the network more usable for everyone else. So the Tor network, Tor is an anonymous communication network. So clients can use Tor to remain anonymous. The way they do this is they send their message through a series of relays called a Tor circuit. The message travels through these relays. These relays are located around the world, and eventually the last relay in the circuit will forward the message to the server. So the server will think this message came from one of the Tor relays, and he won't be able to determine the client's identity. In fact, no single relay in this circuit will be able to determine both the client and the server. Okay, so this client and the server remain unlinkable. So it's a little bit more detailed than that. Tor actually contains what are called guard relays. Guard relays are relays that the client will select to use as their first hop into the Tor network. These are also called entry nodes. Okay, so a client will select a small set of these guard nodes, and it will use these guard nodes over and over again as their entry into the Tor network. The idea here is that by using this technique, clients can limit the number of relays that they give out their IP address to, so the number of relays who know their identity. And also this prevents an adversary who controls some guard nodes from doing pseudonymous profiling of a large number of clients. Okay, so guard nodes are used in the network. Okay, so a client will use a guard node for all of its circuits, for a large fraction of its circuits. Okay, so when this happens, a client has a single connection to the guard node, and those circuits are multiplexed over that one connection. So as shown in this picture, the client has a single connection to the guard, and then from there, the circuits can split off into other relays, going to different destinations. Okay, so currently in the Tor software, Tor has the ability to throttle, the guard node has the ability to throttle the client on this single connection from the guard to the client. Okay, so the guard node can choose to throttle. In the current version of Tor, the guard node has to adjust throttling by setting the throttling parameters, both the token bucket rate and the bandwidth rate and the bandwidth burst. So the size of the token bucket and how fast the token bucket gets refilled. Okay, so he can use this to throttle the client. Now, throttling is not enabled by default in the current version of Tor. So we would like to explore throttling algorithms that work adaptively. So the static throttling approach may be good for certain settings, may be good for certain guard nodes, but it's not clear that those settings will work for everyone. So we would like to explore an adaptive algorithm that takes care of the following criteria. The guard node, since the guard node services multiple clients, okay, he has to determine which of the clients, which connections should he throttle. He also has to answer the question of at what rate should he throttle those connections. Okay, and in our approaches, we would like to solve this problem. We would like to come up with an algorithm that follows the constraint of only using local information, right? So the guard node doesn't communicate with other relays to determine who he should throttle. He uses only information that he already has. Okay. So our approach, we came up with three algorithms for achieving three throttling algorithms to throttle clients on this connection adaptively. So the first algorithm looks at adaptively adjusting the throttle rate. Okay, we call this the bit splitting algorithm. In this algorithm, the guard node will split up his bandwidth resources evenly among all the connections to the clients. So if he has a 100 kilobyte connection, for example, and he has 100 clients, he will throttle each of those connections to the clients at 1 kilobyte per second. This is a fairly naive approach, and in fact, many ISPs use this idea of fair splitting to throttle clients, to throttle their customers. A second approach is to adaptively select the connections. So in this approach, we no longer adaptively adjust the throttle rate, but only the connections. The idea here is that if we can flag the connections that are using a large majority of bandwidth, or if we can flag the bulk connections, we can throttle them aggressively, and effectively we can prevent a lot of bytes from ever entering the Tor network in the first place and congesting up other relays. So the idea here is that if we can keep those bytes off the network, even though a specific guard node might have enough bandwidth to handle those bytes, by keeping those off the network, he's helping other relays somewhere downstream who may be congested or maybe a bottleneck for a certain circuit. Okay. Finally, we come up with a third algorithm that we call the threshold algorithm. This algorithm looks at both the throttle rate and the connections that are selected to throttle. The way this throttling algorithm works, the threshold algorithm works, is by selecting the lowest fraction of connections. Okay, so for example, if a guard node has 100 connections and he's throttling the top 10%, he will throttle the lowest 10% of those connections. And the rate at which he throttles them is the slowest measured throughput of those lowest 10%. So we simulated these algorithms in the Shadow Simulator. The Shadow Simulator is published at NDSS 2012. You can take a look at that in the resources. So we use the same model that we designed in the Shadow work. Namely, we have 950 web clients, 50 bulk clients, and 50 relays. Okay, and our network is set up to model the live Tor network using data collected from the live network. So we simulated vanilla Tor with no throttling. That's the solid black line. We simulated the static throttling approach, which, as I mentioned earlier, exists in Tor today, but requires you to set specific parameters. And we throttled each of the three algorithms that I just described. Okay, so as we can see, web client performance increases dramatically for all of these throttling approaches. The static throttling approach does the worst of the throttling approaches, and the threshold and flagging algorithm performs the best for clients. We can also see here that bulk client performance does get worse because we are in fact throttling people who are sending too much data into the network. So we expect bulk performance to decrease. But remember that we're throttling a small fraction of the entire population of clients on the network, and this is going to yield much improved performance for the rest of the users of the network. Okay. Another thing I want to point out here is that we did several simulations over varying traffic loads on the network. The graphs aren't shown here, but we found that for static throttling, when the network load changes, it's hard to get the correct setting again. Once you find the setting for your particular network, it seems to perform okay, as we can see in these graphs for web client performance. But as the network load changes, as the network dynamics change, then you have to readjust those settings, whereas our other adaptive algorithms essentially adjust themselves as the network changes. Okay, so we've shown that these throttling algorithms are a clear winner in terms of performance. We also look at how throttling affects anonymity. So an adversary can potentially learn two things from a guard node who is throttling. He might be able to learn the throttle rate of the guard node. So at what rate is the guard node throttling a particular circuit or a particular connection? So if he can learn that throttle rate, then he can reduce his uncertainty about a given connection. So the information that he loses from this is shown on the graph on the right. Okay. We also compare this to vanilla Tor because even you can do the same type of attack on the real Tor network without throttling. Okay. So we can see that static throttling, the red line, performs the best because all of the connections look exactly the same, so you leak the least amount of information. And a lot of the algorithms, at worst, the throttling algorithms perform about the same as vanilla Tor. Okay. But in general, it performs slightly better. On the left graph, we're seeing what an adversary can learn given that he knows the throughput of the circuit. So essentially, if the adversary controls a server and he can determine the throughput of a circuit, how can he reduce the set of potential guard nodes that could be at the other end of the circuit, right? So in order to reduce his uncertainty about the guard node, he can test the throughput of the circuit and try to determine this. So the information lost using the throughput of the circuit is given on the left graph. And as we can see, again, static throttling performs the best because all the connections look the same. And each of the throttling algorithms performs better than vanilla Tor with no throttling. Again, because in each of these cases, we are throttling connections so that they look similar to other connections that are also getting throttled. So this leaks less information. Okay, so just to summarize quickly, our goal in this work is to throttle the bandwidth parasites. Really, the small percentage of users who are making things horrible for everyone else. Okay, we propose and analyze 3 throttling algorithms for Tor, and we show that they dramatically increase performance while also improving anonymity at the same time. Finally, our algorithms are written as are implemented into the real Tor software, and patches are publicly available on my GitHub site. So you can contact me if you have further questions. As I mentioned, the algorithms are available. They're implemented in Tor on my GitHub site at github.com/RobGJansen. Our simulator is available at github.com/shadow and also shadow.cs.umn.edu. Thanks for listening.